Yeah, hello. So we've written the software for a closed loop laser beam stabilization system, um, and what it does is it stabilizes the beam in 4 dimensions. So we want to have a look and how it looks like. Um, it takes in the laser from here, sends it through four different mirrors more than 4 different mirrors. 2 manual mirrors, then 2 motorized mirrors. It goes through a beam sampler here, and another beam sampler there, and then you get 2 spots on the camera, and these 2 represent both position and angle. And then once it goes through that one, it also goes to another detector, so the quadrant photodiode, and then you have another way to actually compare how well the beam is correcting not only on the camera but also on the quadrant photodiode, because then you'd have two different ways to see and correct the beam. So let's have a look at how well it stabilizes the beam in 4 different dimensions. So the beam right now is at 0, 0, so that's sort of the centering that it has. So it's a quadrant photodiode, so it has 4 different regions. So let's say the reference point is going to be at -4. So if I correct it here, it should approach the 4 that we had originally been at.
Because anyway, not too much encouraging that bodies to work.
Yeah, but you said something was broken.
Yeah, one, but I don't know what's.
But yeah, it's generally on the graph you can see it's relatively stabilized. It hasn't reached the 4 that we were at, but maybe that was the reference position. So it's dependent on the reference position that was taken at the beginning, which would have been 15. So if I move it again, it should probably go with 15 now.
On this one. You will not to shallow state, but it takes some time.
Well,
It takes some time to.
now it's back at 0. I guess it.
The system.
Yeah, but essentially it stabilizes the beam back to the initial target positions that were set at the beginning, and it seems to fluctuate sometimes between the reference points. Yeah. Hi, so I'm just here documenting my laser stabilization software, or the active beam stabilization software. So sort of what has been developed is I've got a detection, so you can modify the threshold value of the detection settings. So the spots can be having a sort of value that they can be detected below or above. And if they don't meet the threshold, then they aren't detected anymore, which can be useful if there are many spots on the screen, or you just want to have less spots. There's also the contrast as well, which is a useful function, which can then make the spots, because the spots are not very bright at all, it's necessary to actually add significant contrast and brightness to actually make the spots visible. Otherwise, it can't be seen. But yeah, this is the functionality that enables it. And so, yeah, there's contrasting and brightness and thresholding that's used for the detection of the beam spots. Then also for the user interface itself, there's the target setting. So the beams can be set to their specific targets, for instance here. And there is a highlight that indicates essentially how far the spots are from the beam. So yeah, and then this information, and you can also switch between the 2 spots. Why is this information useful? Well, it's because knowing the distance and the error between the 2 spots gives us an indication of how much the beam stabilization system software needs to correct. And yeah. So there's also an option to jog the motors as well. And then also to characterize the motors as well. So the motors are non-linear, or non-linear pico open loop pico motors, which means that the steps you'll need generally a pretty good matrix that can characterize it, and the matrix only really works over a very short distance. So this is why characterization is so important. But essentially loops over the 4 different axes and performs 9 different steps, and then outputs exactly to the user as a sort of graph. Outputs, what sort of responses are from the motors. So you have the different motor steps. They go from -100 to 0, and so you can see, for instance, for the first axis, you just moved this specific motor from a motor step from 0 to -100 and back and forth. So just moving them back and forth, and you can see how much the pixels have changed. So the pixels seem to change a bit more for axis 1 and 2. So and that could be because it's a motor that is that controls the position, so the position has a much more significant impact on where the beam spot is, as it affects both the upstream and the downstream spots. So yeah, that makes sense. And then you have the second axis that also controls the pixel position of the beam quite a lot, and so that also determines where your beam's going to be. And then also for your third, there's the motor steps as well. This is just a bit less, but you can see that all of the sort of dx, dy positions are sort of controlled by the different axes. So, for instance, the y-axis for the second spot is controlled largely by the third axis of the 4 different actuators. The y dimension of the second spot is largely determined by the first axis, and then for the second spot, the change in position of the x axis is largely determined by the second axis. So, and then same goes for the y position. I guess that nothing seems to really control the axis for the first spot. But that might just be due to noise or other filtering issues, and so there's many things that could be causing this this spot not actually being that functional. But yeah, that's sort of what to look into. But yeah, this is essentially the software that characterizes how the actuators respond to pixels to motor steps, and this is useful for performing this analysis because then you can determine how well your matrix will be. And yeah, this is all then processed down into a Jacobian. And Jacobian's just for just a matrix that contains linear elements, and then these linear elements then can transform movements, so commands, into errors into actuator commands, because the relationship between the two, the errors and the commands, are non-linear. So that's why the Jacobian matrix is very useful, because it turns it turns non-linear relationships into linear linear transformations. So it's useful mathematical concept. Yeah. What else was there? And yeah. There's also an option now for locking. So now the beam can also lock to its position. So by clicking the lock function, it locks to the position by taking in the value from the error target distance and then corrects it. So you can see it slightly moves towards a spot. So you can see the error decreasing progressively. For instance, target 2, you can see how the error is decreasing, which is, proves that the functionality of the beam locking system works generally pretty well. So here, you can see the error is reduced from 60 to even 24, and it's almost now been corrected. So generally the software works. So for stabilizing any soft beams, the software works. So yeah, thanks for, yeah, this was cool. Thank you.